Good afternoon.
Good afternoon.
I hope everyone had a wonderful wet weekend. And it looks like we're missing some people now. Maybe it's because of weather-related things. So just so you know, we all do record class. I try to post the Word documents and the PowerPoints online right away. And then I also post the YouTube video as soon as I leave class. So the YouTube video captures everything on the screen and the audio coming from that tablet. So if you have the tablet come close to you and you don't want to be heard on the recording, it's just inside of our class. But then just let me know and I'll move the tablet. One thing I wanted to point out was what's appropriate study time? I heard that there's a big variety in the amount of time that people studied this past weekend, completing homework number 3. I heard it was all the way from like 1 hour to like 14 or 15 hours. So what is an appropriate amount of time to try one problem? Appropriate number of times. Sorry?
Before giving up, is that what you're saying?
Before trying something different.
3 times.
3, I'd say 2 to 3, maybe 4 if you think that if it's a multi-part problem, then it's all bets are off, right? But a lot of students will try just like putting the same number in over and over, or try recalculating the same thing over and over. It is not productive. If you have tried one part of a problem 2 or 3 times at most, stop. Do something different. Do you guys all know about the resources that are available through the book? So at the top of your OWL homework, there's a link that says resources, I think. References or resources, 1 and 2. I think there's both there. If you click on one of those, it literally links you directly to that section of the book. So you can go read that. You don't have to use that as a resource. I think it's a good resource that you paid for, so it's worth trying. A lot of times under that link, there's also tutorials or simulations or other things to help you visualize what that problem is getting at. You can Google YouTube videos. You can ask friends in the class. You can post a note to discussions in Blackboard. I get notified immediately. I'm subscribed to all Blackboard threads. If I am close to a computer or a phone that has access to the internet, I will reply as soon as I can. I'm not always the best person to reply, though. Sometimes if you post a picture of your work, like, I just don't get it. Why am I not getting this problem right? I must be missing something. Post a picture of that. One of your peers is probably going to pop on there as well. We have a number of people who go check that forum fairly frequently. And they might say, oh, it looks like you solved for this part, but you haven't gotten to the final answer yet. That fits into the bigger picture. Something like that. So basically, if you spend, I would say I would approximate every week to spend a maximum of 3 to 4 hours on the homework. If you start it before the weekend and you get really stuck, I have office hours on Friday afternoon. That's a great time to come. I'm thinking about doing exam review session this Friday instead of office hours, which is essentially office hours, but kind of on steroids with more people, and we kind of break out into groups. So that's 1 to 2:30. What time are office hours on Friday? 1 to 2:30 on Fridays. Would anyone be interested in coming to an exam review session, because we do have an exam next week? Raise your hand if you're interested and able to come to that time slot. Okay, so there's enough people that you won't fit in my science lab office. So I have another office that's, if you get open this door and see the corner of ETAS, it's that corner of the building, first floor. ETAS 125. We'll hold office hours there, exam review session on Friday, 1 to 2:30. Come with a particular topic that you have trouble working on, and we'll work on it together. I'll have some questions also I can pull, and we can work on those problems. We can split it into different groups if we have different focuses we want to work on. All right. Any questions on appropriate amount of time to study, what to do when you get stuck, these kinds of bigger picture things? I do ask a decent amount. I think other professors would say that they ask the same amount, but they don't require it. I think that you can't benefit from the work if you don't do it, so I don't suggest things unless I require them for the most part. Every once in a while I'll add a couple things, say this is an extra resource in case you're stuck. So hopefully you find that the work that you're doing is actually helping you understand the topics that we're working on. Speaking of which, here's a great example of a question that I want you to be able to answer at this point in the semester. We have the distribution of all 3 answers. turn and talk to your neighbor, try to figure out whether we can answer this. And when I say we, we're not in a test situation, right? We're here in this class, sitting with all the resources that we have. Can we answer this question? And I'm not saying Google the answer. I'm saying what resources can we access that we might not have in front of us?
Let's see.
It's representing now how much semester's going on.
So is question C the correct answer? Is answer C the right answer to this question?
No.
No. Why?
Because we do have resources that we could use.
What resource might we use in order to help answer this question?
Our cellular devices.
And what would they help us find?
The freezing point of acetaminophen, whatever it's called. Whatever it's called.
Well,
You know,
is acetaminophen, which is also called Tylenol,
Yeah.
is that our solute or our solvent? Solute. So what do we need to find the freezing point of? Which is our solvent. If we're feeding it to a baby, I hope the solvent's water, because other solvents would be either toxic or, well, no matter what, they'd be toxic. Okay? We're not going to give them ethanol as a solvent.
Either way.
We're not going to give them chloroform, ether, any of these other solvents you guys have been thinking about. Alright, it is water. Water is the solvent of life. Alright, so do we know the freezing point of water?
Yes.
What is it? 0 degrees Celsius, okay? So we know the freezing point is the solvent. We know the freezing point of the solution. What are we missing, though? What's something that we need in order to answer a question like this, Josh?
We were just talking about the Kelvin temperature.
There. What do we need? What is imperative, Matt?
The molecular weight of
Is that something we can find? Yes. Why would we want to know the molecular weight of acetaminophen? Molality? Yes. So with the molar weight, we can find the number of moles of our solute. Do we want molarity or molality? Molality. Alright. You guys can do that, right?
Yes.
What's the one piece of information you're missing?
Molar mass.
Well, you can look up the molar mass, right? We said that. So there's one other piece of information that I probably should have included.
K of it.
Right, so you can Google the constants. All right, let's go ahead and do it, and then we'll come. You'll figure out when we come to that part what the other thing is that I actually will probably need to give you. Sorry, I thought that was you running. I saw it upside down.
Did they answer your question?
By the way, if you wanted to turn in your Chem Activity 10 as one of your 3 out of 4 supplemental instructions, please do that now, not at the end of class.
Yes. Oh, the K is
And then we know that K of freezing for water is
More than one thing. The average dose. That is actually out of that. I gotta get this in a look it up. Alright, wow. It's almost the same.
So there's, if I can get everyone's attention for 1 second, there's one change. Probably it's best to say change to the wording instead of one additional piece of information that you guys need. What is the one thing that you're finding that you need that you don't have? So you kind of need either the density of the solution or a couple different ways to look at it. So what I'm going to say is let's simplify this question, and let's say that it's 160 milligrams of acetaminophen in 5.00 mils of water. And then do we know the density of water? If we assume standard temperature, density of water is 1 gram, 1.00 grams per milliliter. All right, I think that's everything you should need. The way the question was worded wasn't the best.
Oh, yeah, I did.
I'm doing okay. They're good. We're figuring it out.
No, dude,
All right, let's take one more minute to work on your own, then we'll work on it together. Make sure you're getting as far as you can, at least have things written out. I'm not as interested in the final answer as if you can write it out nice and clear so we can follow your logic.
Yeah. Water.
it's going to freeze because it's only 160 milligrams. It's like I went to Cal's for and I finished it. I was crunching the last couple I had my test Friday.
All right. If you have a final answer or close, click it in. If you're not changing your answer or you don't know yet, then don't worry about it. I'm just curious to see where the clicker ends up. You might be able to eyeball it too once you get to a certain point in your calculations, because this question is not saying what is the exact freezing point. It's saying is it greater or less than what is in your freezer, minus 18 degrees Celsius. All right. So how do we go about this? Can I have someone maybe volunteer? Let's do a blank screen. Let's do graph. How do we go about this? How do we answer this question? Can I have someone talk me through the steps without the numbers so much? David?
What I did was I converted the 160 megs to moles
Why?
because you got to find the molality.
Okay, why do we need a molality?
Because you can take molality and put it into the
Okay, that is one way we can do this. So the first thing I'd suggest, write down the temperature freezing equation. What is it?
It's KFP times molality times fan
So I'm going to write it out.
Yeah, freezing point potential and molality.
Okay.
And so from there, I got my moles, and then I converted the 5 milliliters into kilograms.
Okay, so if we know it's water, 5.00 milliliters, we can convert that into mass. How'd you do that?
So what I did, I actually looked it up. This ends up being 5 kilograms. So it cancels out.
5 kilograms?
Yeah, I'm sorry.
And we could all do this in one line. So I know that, is a gram smaller than a kilogram or a kilogram smaller than a gram? So we know we have 1,000 grams in 1 kilogram, so we could write that all out. 5.00 times 10 to the negative third kilograms.
Yeah,
All right.
and then found the molality from that, which is the moles per gram.
Did anyone else write this out as well?
Yes.
So I think, for me, I would always write out the equation we're trying to get to. What part of that are we trying to solve for right now? Because could we look up any of those things already? Can we look up I for acetaminophen? What did you guys find? 1. KF, can we find that? Is that for acetaminophen, or what is that for?
That's for the water.
It's for the solvent. All right, so we can look those two things up. So we only need to find molality. If we find the moles of our solute, then we can answer this question. So that's really where we're going. All right, so we know the kilograms of our solvent. How do you find the moles of our solute? Can I hear from someone else? Can I get maybe Aaron? How did you find the moles of solute? Did you find the moles of solute yet?
Okay, so what I did first was I looked up the molecular weight statement, and I found it to be 1.163 grams, and I converted 160 milligrams to grams, and then I used the molar mass to convert to
151 point.
160.
I'm just going to do ACT for now as an abbreviation. And how many moles did you find we have?
0.00105.
Okay. And we probably want to store whatever that value is and use the stored number in our calculation so we don't propagate rounding of numbers. Okay? Can we find the molality now? It's all about the ratio. So you did some problems in your homework. They were all about finding, if we find grams and moles, we can find the ratio, and that's the molar mass. Matt?
How did you go straight from milligrams to just moles?
Oh, did you tell me the number of millimoles or number of moles? Good catch.
No, I said the number of moles.
Okay, great.
So I used the conversion factor from grams.
So now that I know that and I'm paying attention, I would have answered this as 1.05 something times 10 to the negative third moles. How did I do that? What did I substitute there? What does milli mean? 1,000th times 10 to the negative third. Is milli. Milli is 10 to the negative third. So I could have written milli here. I could have written 10 to the times 10 to the negative third. Either one's fine. Or the way that you wrote it out, which was 0.00105. I much prefer scientific notation. I will use scientific notation in my examples. So make sure you're comfortable with matching those up. If you're not, please come to office hours. We can work through and I can show you how that works. I think we can get you pretty comfortable if that's something we focus on. All right, so now we know how many moles of acetaminophen. We know how many kilograms. Can we find molality? Find the ratio between the two. And then the Van Hoff factor for acetaminophen. Is that something we can just know by the name? We might assume, but we don't know. So did anyone figure that out? How do you figure it out, Moab?
I was gonna Google it, but the kind PA here, I was like, look, instead of me Googling it, can you just tell me the formula? And it didn't have any ions in it, so I knew that it was 1. He didn't give me the answer, but
Yeah, fair enough. So you could Google it, you can see the formula. It only has carbon, hydrogen, oxygen. Does that have nitrogen?
Yeah, there's a nitrogen. It was NO2 at the end. It kind of tripped me up.
Okay.
I was like,
So it doesn't have any ionic bonds as far as we can tell. You can look at the structure, be an even better way. So if you Google acetaminophen, it'll pop up the structure. You look at the structure, you can say, are there any ionic bonds? Yes or no. If not, then the Van Hoff factor is 1. All right. So then if we plug all those things into our beautiful relationship here called an equation, can I hear from Lindsay? What did you find for your delta TF? Units. Which one is it? Which one is it? Which one is it? So KF, the units are really important. It's 1.86 degrees Celsius per molal. I don't use a negative KF. I know a lot of people want to use a negative KF because it tells you this. So I would actually have gotten delta TF is 0.39 degrees Celsius. Why? What's your question?
I got 0.039.
Is it 0.039 or 0.39?
I got 0.9.
Sounds like the overwhelming majority disagrees with your scientific notation. Okay. So, is the change in freezing point ever going to be an increase to the freezing point?
No.
No. I would much rather you don't use a sign for KF or KB, and then say KB, the boiling point always goes up, KF, the freezing point always goes down, and then use that from our reference value to go in the right direction. That means you actually understand it more than just plugging numbers into an equation. All right, so from this, can we answer the question? What would that number have to be in order for this question to be answered differently? At least 18 degrees Celsius, because we know 0 is the starting point, degrees Celsius. It would have to decrease more than 18 degrees Celsius, and there's no way that that's going to happen with these numbers. Did anyone answer this question another way? No one? How could we answer this question another way besides these calculations that we just did? Echo?
well, once we found out that water was the solvent, I kind of knew it was going to freeze if it was anything under, right around that 0 degree. Is that the question? Sorry.
I think the question I'm getting at is, how do we figure out what this is so far off from 18 degrees Celsius, but we could have answered that by going backwards. So what if I said delta TF is 18 degrees Celsius, and then I backed out how much mass you would have to dissolve in 5 milliliters? Do you see how we could do that? In that case, we would be solving for the mass. We could go backwards through all those calculations. I'm just saying there's another way to do this, right? You'd say how much mass, how much solute would I have to add in order to get to an 18-degree decrease in freezing point? All right? So I just want to point out that these questions don't have to be answered only in one way. So that would be a very good example of an exam question for next week, next Wednesday. I expect you to be able to not only plug numbers into a calculator, which by itself can be challenging, I also expect you to be able to use that to answer a logical question. And if the question was worded just like this, and it was a multiple choice question, think about how concentrated that sample would have to be in order to freeze at 18 degrees Celsius. So we could have looked at this and said, okay, well, if I know this equation has 1.86 there, what would I have to multiply it by molality-wise to get an 18-degree temperature difference? It's going to have to be a big number, right? It's going to have to be like 9 molo. You guys see where I'm getting at? If this is almost 2, then this would have to be about 9 to get about 18 here. Right? So that's kind of where I was going down here by saying if we had that. You could answer that question within 30 seconds if you understood what that equation told you and how those variables fit together. And on an exam, you wouldn't have to show me the work. You would just have to be able to say, well, that doesn't make sense. You can go back later if you have time and calculate those numbers to verify your answer. You have a question, David?
I was just going to say, I didn't get 139, but I still got
A number smaller?
Yeah.
Okay. So I can look at it when I'm walking around later and see where you might have differed. So what temperature does this solution actually freeze at? All right, negative 0.39. Well, look at your calculations to see if that's off. How many sig figs should we have?
3, right? Or no?
How many sig figs are here? 2. And then I can't remember what I wrote here, 5.00 milliliters maybe. So this would be limited to 2 sig figs. If I had a decimal after the 0, saying that's exactly 160 milligrams, that would be 3 sig figs, and that would be our answer. All right, so our learning objectives for today, and for those who were not in my class before, just a reminder that these are your study guide for the exam. Go back through, look over all the learning objectives. That is what you need to be able to do for the exam. So calculate changes in boiling point and freezing point after the addition of solute to pure solvent. We're going to do a little bit of conversion between units of concentration, and we're going to calculate osmotic pressure today. For next class, we're going to be building on what you guys did in the homework. It sounds like it was a little bit rough, but we want to figure out what the identity of an unknown is through all the different types of colligative properties, and we could throw Raoult's law and vapor pressure in there as well. All right. What do you guys think about this question? I think we're on to question number 2, 35 minutes in. It's not multiple choice, recall. I want you to enter the number of any of these that could be possible. And no, you should not need to Google any of these. The only one you might want to Google is the first one if you don't know that. The other ones you should, let's just say you should be able to identify the formula for those without Googling them. Just do what you got to do and use that as a reminder that you might need to learn something. So if you think it's 2, 3, and 4, type in 234. If you think it's 1 and 3, type in 13. Alright, we only have 24 responses. That means that if you're not feeling comfortable, you need to raise your hand. Have one of us come chat with you. And remember, after you've entered your number, you have to hit send, or else it won't send it.
So I'm just curious about calcium phosphate. I just don't.
All right, if you're not familiar with acetone, hopefully you guys wrote down all the formulas or structures of all these. Acetone is, I'll go ahead and draw that one out. Is that molecular, ionic, or both? Molecular. There's 3 carbons, there's 6 hydrogens, and 1 oxygen. All right. Sodium chloride. Can I get a formula for each of these as we go forward? All right, sodium sulfate. Carol, what's sodium sulfate's formula?
N2SO4.
Okay, and calcium phosphate. Savannah?
CA3, and then parentheses PO4, parentheses 2.
Okay, does everybody agree with these? All right, so if this is something you're rusty on, please go spend a little bit of time, come to office hours, chat about it with your TA, tutoring, whatever you want. Sodium has a +1, sulfate has a -2, so we need 2 sulfates for every 1 2 sodiums for every sulfate. Calcium is a +2, phosphate is a -3, so we have 3 minus, 2 plus, have to have a total of 6 plus and 6 minus. Is this molecular, ionic, or both? Sodium sulfate. It's ionic because we have a plus and a minus, but this is a molecule, so it's both molecular and ionic. Calcium phosphate? Both as well. All right. So then what is our predicted, our theoretical Van Hoff factor for each of these? Let's start at the top. Acetone, theoretical Van Hoff factor.
1.
If it does dissolve, it would be 1. Sodium chloride.
2.
Sodium sulfate.
3.
Calcium phosphate. 3 calciums, 2 phosphates. So, which one is it? Which one can it be? So the question is, which compounds could this be? So it's not 3. It's 2.8. So how can it be this one?
We rounded.
Anthony, what are your thoughts?
Oh, it's just theoretical. It doesn't mean that's...
Right, so how can the theoretical be off from the experimental? What's going on?
Because they form.
Love, what's your thought?
Not all the molecules dissolve.
They don't all dissolve, or they don't dissolve fully. So either way, I think maybe the way you said it's a little clearer, in that you have 1,000 of them. At one point in time, you're going to have a small subset that aren't separated, that are together. And then you're going to have most of them that are separated. If it was calcium phosphate, what would that tell us about that compound? How much of the time is it dissolved, and how much of the time, or how many of them, what fraction of them are dissolved, what fraction are not? About half. Yeah. And so this question, either of these would be an appropriate answer, that both of these could be this compound, because they don't fully dissolve. But there's no way that this could be acetone or sodium chloride. And so that idea of compounds not fully dissociating kind of brings us back to the solubility table that we used in first semester. Most of us, some of us did. So this table basically is something that we use to say what are the anions And what are they paired with? So sodium chloride is this square right here. It's white, so that means it's soluble. Magnesium hydroxide is gray. It is insoluble. This isn't black and white, right? Just like the theoretical Van Hoff factor of 3 of sodium sulfate isn't actually found experimentally. That means that this might actually be that some of it does separate, but a very small amount of it does. Versus these ones, it might be, instead of a Van Hoff factor of 2, we might actually find a 1.8. Okay?
Is there an amount that, you know, like leaves separated or up to an amount that it dissolves where it's considered like soluble or not?
Yeah, so this particular table, they describe insoluble as less than 0.05 molar concentration. If you have less than 0.05 molar concentration, then it doesn't dissolve. But that's a pretty low concentration. So honestly, a lot of these that say soluble, you'll have a Van Hoff factor that's much lower than the theoretical. All right, this is a practice problem that you guys can do on your own. This is another exam-like question. Basically, is this molecule ionic or not? You're given a whole bunch of information. You have to figure that out on your own. All right, we're not going to do that right now in class, but you can come back to the slides. I think it's also listed in the homework in the worksheet. So you can go ahead and practice that. All right, so I want you guys looking at this figure. It's at the bottom of page 1. I want you first on your own to look at this graph and see what's different from the other phase diagrams we've looked at. Once you've thought about it on your own and identified what it's trying to show you, what's different about it, then I want you to pair and talk to the person next to you to try to identify what's different between this phase diagram and the other one that we've seen. All right, can I hear from Marlene? What do you see in this graph this figure that's different from ones you've seen before?
Well, it's showing the solute and the solution and the solvent, and it's showing like the solids, liquids, and gases as well.
Okay, so similar to the ones before, you're identifying it's showing solids, liquids, and gases. But then what did you say about solutes?
It's showing the like the solutions and the solvent.
So which is the solution, which is the solvent? Do you want to draw on the tablet?
What is it? Would it be like that?
So what is the solution pointing at, and what is the solvent pointing at?
The solids and the gas?
So if we kind of build off of what Marlene's saying, that's pointing to that line right there. So the solid black line that's separating all these, those are the properties of the pure solvent. What happens to all those properties when you add a solute and make a solution? What do you mean it's distorted?
It's the boiling points, at least on that one, it's showing that it's increasing. It's showing that there's that additional IMF going on, so it increased that boiling point as well as the freezing point. In comparison to just the solvent by itself.
So if we look just at 1 atmosphere, we can see that the freezing point decreased, and we can see that the boiling point increased. So I wanted to show this diagram to you guys because I think it's actually a useful way. If you ever forget which way boiling point and freezing points change when you add a solute, this is how I picture it in my head. I see the 2 lines, pure solvent, and then the solutions move further away. If you remember what the axes are on this graph, it can kind of help you orient what changes you expect for solvent versus solution for freezing and boiling points. So it really is just trying to emphasize the boiling point elevation and the freezing point depression. So we've talked about a number of these. I want to point out one very important distinction when we're looking at these different colligative properties. The top 3 of them are temperature dependent. What that means is you're never going to see what unit of concentration does not depend on the volume. Let's say it's the other way around. Is there a form of concentration that depends on the volume of the solution or the solvent? Molarity. Molarity is over the liters of solution. As you warm and cool up solutions, you do have a slight change in volume. So for these 3, we're never going to use molarity. In the equation for vapor pressure, what form of concentration are we using? For vapor pressure, you guys did some homework problems on this last night.
It's the mole fraction.
Mole fraction. The number of moles don't change of the solute or the solvent or the total. That doesn't change based on expanding or contracting. So this is going to be not dependent on the volume. What do we use for boiling point elevation? What form of concentration do we use for that? Molality. And for melting point? What about osmotic pressure? Is that the same? That one actually has temperature built into the equation, and so we're going to use molarity for that. So these 3, we want to be very careful that the expansion and contraction isn't accounted for in our concentration units. That's why we use mole fraction and molality. All right, so let's spend a minute with one of the forms of concentration we haven't talked about much yet. And then we'll talk about osmotic pressure. Go ahead and make your selection. What makes the most sense? We have a mix of answers. If your mother or your father or your brother asks you to go make a 0.9% solution of sodium chloride, how would you go measure out your sodium chloride? What happens if you have sea salt versus coarsely ground salt? Would that differ? Would that change your percent volume? So many people said percent volume, we measure in a cup, right? Cup measure. But depending on what type of salt you have, where it originated from, how it crystallized, the volume of that's going to be different. So to make sure we have consistency, we would weigh that out based on mass. So So 0.9% of the mass of a saline solution is sodium chloride. As a chemist, this is very frustrating. What does it tell you? 0.9%? I have no idea how much that actually is. Like, I want to know the molar concentration, the mole, or the mole fraction, or something that actually relates to like how much is there, as opposed to how much it weighs. But this is a very, very common form of concentration used in medicine. It's much easier to handle and to make, much easier for people to understand who don't understand what the mole is. So you guys need to know how to use this. So go ahead and determine what mass of sodium chloride you'd have to add.
Okay, so yeah, but so we're working back backwards, right? So we back, so we got it. So no, you just
It doesn't say it on there.
But it has 500
milliliters. Huh? So you convert that to mass. Remember, it's in water, so it's water. Okay. So I have it in milliliters. And then use that.
All right. Can I hear from the group of 4 in the back, please? How did you solve this problem?
Okay, so I used the mass percent equation, and skip on that, I got 4.54 grams, unless I'm wrong.
Okay. One of the really important things I want you guys to do is approximating first. how can we approximate a question like this? Okay, so what would it be if it was out of 1,000?
Are you asking me? Or
Sure,
Oh.
if you're throwing it out there.
It would be 9. Yeah.
9. Okay. So we want to think about, what does 0.9% mean? 0.9% means just a little bit less than 1%. So it's just a little less than 1% of the mass. So if I was to approximate, I could say, well, let me use a round number. I could use, if it was 100 grams, I would say that this was about 1 gram, right? More specifically, it would be 0.9 grams of NaCl. Ah, that's not what I wanted. Is that something you guys feel like you can do? For percent mass, and anytime we use percent, people get way hung up in like how to try to show it mathematically. And if you don't do the logic check first, then you end up just jumbling a whole bunch of numbers together, and I get some wacky numbers that get thrown out, all right? So I'm not saying your number was wacky, your number was actually pretty spot on, but I want you to have a logic check first to make sure that however you use an equation, if you use an equation, that it makes sense in the end. So in this case, we know that it was 500 milliliters of water. And then we don't know mass. Do we know mass? How do we convert from volume to mass? So we can probably assume it's close enough to the density of water. So we know that we have 500 grams of water, or a solution in this case. What's 1% of 500? 5. So whatever answer we come up with, it better be close to 5 units? Grams. 5 grams of sodium chloride. All right? And so then you can use whatever equation you want. I don't care. All right? So I would probably do it 500 grams times 0.009. I don't know what equation that is. I would just use logic to figure it out. The other way you can do it is a percentage is parts out of 100. So 0.9 parts out of 100. This is the conversion factor that a lot of you were trying to figure out. 0.9 grams percent mass, right? Out of 100 grams of solution. That's the conversion factor you can use. All right. Let's move on and have you guys explore some osmotic pressure stuff. So the pre-class assignment, I think, is going to be some mathematical. We're going to do a lot of mathematical stuff on Wednesday. To start with, I want us in the mindset of osmotic pressure. Does anyone know what this kind of device is called, where you have this U-shaped tube that has water on both sides and a semi-permeable membrane in the middle? Anybody? What? Not quite. I don't know what a udiometer, if that is another name for it. It's, anyone like the Muppets? Manometer? Manometer. Manometer. I love the name of it. It's awesome. All right, so if we have two different solutions, semi-permeable membrane, that just means that there's some sort of barrier that some things can go back and forth through it. Typically, the things that can go back and forth through it are water, so Gore-Tex is an example of a semi-permeable membrane. Shell around an egg, not the shell, but the inner membrane is an example of this. So if we have 2 molar sodium chloride on the left side, on the right side we have 0.1 molar sodium chloride. We pour both of those in, we walk away for half an hour, and we come back. Which side, if either, will the water level rise in? Knowing that water flows freely back and forth between both sides of the semi-permeable membrane. So go ahead and click in your answer. All right, click in your response. And we're coming back to it. So let's start. I'm gonna show a video, walk through a couple things. We'll come back to the end. All right. What has a higher concentration of solutes? Water or corn syrup? Go ahead and click in your response just to that question. Click in your response, please. Those of you who don't know what corn syrup is, it's that stuff that Budweiser is no longer using in their beer. True. All right. What is the major component of corn syrup? Some kinds of sugar, right? Lots and lots and lots of sugar. So I just want to get on the same page about that. So let's go ahead and watch a little video. And I want you guys, let's see if we can get the volume on and up.
Which protects the semi-permeable inner membrane. This membrane is semi-permeable because it allows substances to leave and some substances to enter. In particular, the semi-permeable membrane allows water to both enter and leave the cell, but large molecules, like salt or sugar, are too big to pass through. The question is, how can we examine the semi-permeable qualities of this inner membrane with the hard eggshell in the way?
Science.
Dissolve the outer shell by placing an egg in vinegar. Vinegar has a chemical called acetic acid. Eggshells contain calcium carbonate. When calcium carbonate in the eggshell comes in contact with acetic acid, a chemical reaction occurs. Calcium carbonate will break down to form carbon dioxide, water, and calcium acetate, thus dissolving the calcium carbonate shell. Within seconds, you'll see bubbles form. These bubbles are carbon dioxide that are produced when acetic acid breaks down the eggshell. Within 3 days, you should have a semi-permeable membrane, free of the hard outer shell, to conduct your experiment. Before starting our experiment, we will first mass our egg using a scale. Egg A has a mass of 94 grams. Egg B has a mass of 103 grams. Egg A we will place in a hypotonic solution, water. Egg B we will place in a hypertonic solution, thick and sugary corn syrup.
So let's make a prediction. What do you think is going to happen to the egg in the hypotonic solution? Go ahead and click in your response. Once you've clicked in your response, check with your neighbor. Your own answer first.
But hey.
A couple more clicks. Make your prediction for the second one. What happens to the second egg that's in corn syrup? Click in your response. Then check with your neighbor. You can change after you check. Closing out. All right, want to see if you guys are right?
Egg A now has a mass of 97 grams. Egg A increased slightly to 103% of its original weight. We can conclude when a semi-permeable cell is in a hypotonic solution, water will enter the cell.
You guys like that conclusion?
Egg B now has a mass of 59 grams. Egg B decreased to 57% of its original weight.
Which one of those two is more convincing? So if we're thinking about scientists, right? We have a scientist hat on. What's the problem with that first one? There's barely any change, right? 103% of this original. Well, what if that's just like the scale is error or something like that, right? So then how would you test her conclusions? What would be a really easy way? Talk to your neighbor for a second. How do you test her conclusions with the setup that she's got? All right. I'd like Kalia to share her brilliant insight.
Yes. If you just switch them?
What would you expect to happen if you switched the eggs?
The opposite. Well, hypothetically, theoretically, I mean, you would want to see that the egg that didn't really gain any weight would lose any, to see if your hypothesis was
We can definitely conclude that when a cell is in a hypertonic solution, water will leave the cell. In fact, this is evident by the layer of water sitting on top of the corn syrup. However, 103% change in mass is not very significant. So how about we try this experiment again, but switch the eggs? This time, egg A is going to the hypertonic solution, which is still on the right. Egg B is going in the hypotonic solution, which is still on the left.
Prove it. They're just like
After several hours, mash your eggs again. Egg A went from 97 grams to 55 grams. Egg A has decreased to 57% of its original weight. Egg B went from 59 grams to a whopping 105 grams. Egg B has increased in weight to 177%. In this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters a cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically, salt water, water will leave the cell.
So I think one of the big takeaways that I want us thinking about with osmotic pressure is, once again, the molecular view. So let's take that molecular view that we just saw from that amazing experiment that our scientists did and our scientists would have done. You guys would have figured out how to do this, I'm sure, given enough time. Let's go back and think about this design right here. Right? So instead of having corn syrup and water and an inside of an egg and outside of an egg, let's go back to this simple scenario here where we have two different concentrations of water with sodium chloride in them. Do you remember what your predictions were for this? Mm-hmm. And the manometer? So let's look at what happens. So on the molecular level, we have water that goes from the area with the least solute concentration to the most solute concentration. So the osmotic pressure, it's kind of a weird way to describe this in some ways. But the osmotic pressure is related to gas laws. And it says that if we had a plunger here, how much pressure would we have to apply to this plunger to equalize out the force that acted to push the water up? That's osmotic pressure. It's kind of a weird way of looking at it, right? But that's kind of our artificial way of looking at it. Why does osmotic pressure matter for the careers you guys are interested in? Does it?
Yes. Oh, yeah.
Why? What's an example?
Absorption rate of medication.
stick water in somebody's body.
And?
When they
So it turns out that eggs are very much like red blood cells in some ways. Red blood cells are semi-permeable membranes, but they are not nearly as burly as eggs. And that if we'd had red blood cells in that left container with the water, they would have exploded and it would have just been a whole bright red mess. So they don't just expand and hold the tension, they can't hold that much pressure. What happens the other way around? What happens if your blood gets too thick? Your blood ends up having too high solute concentrations. What happens to your blood cells? Why is that a problem? They don't explode, right? So what happens to them?
They can't carry the oxygen.
Okay, so it becomes challenging to get oxygen around. Yes and no. Sickle cell's a different thing, but maybe some deformities overlap. But think about where all your veins and arteries kink. You end up with these blood cells that aren't round anymore, they get stuck because they're more jagged. So you can get clotting, you can get a whole bunch of other issues that come with blood getting stuck in certain areas where it normally gets filtered and just passes right through. So in the last 3 minutes, we're going to talk this over and then have you guys do one calculation. The top is the ideal gas law. The bottom is your osmotic pressure equation. I want you to tell me how they're related. Talk to your neighbor, look at those two equations.
You got the same temperature.
What's that? Austin, are you willing to share your group's discussion about how those two equations are related?
All we discussed were R and T, really. The constant and then,
Okay, so you said that both of them have R and T. R and T. Any other relationships? Love.
I said molarity, because you can also technically find molarity in the first equation. What would be the N over V?
Moles of solute over liters of solution. Molarity. Okay? So then, what is left as different? So osmotic pressure is defined as pi. That's just the letter that they use. So you're not saying P because it is not a gaseous system. They call osmotic pressure pi. So pi is a symbol instead of saying P.
Is it still the same equivalent in the numbers?
Yeah, so it's atmospheres or torr, millimeters of mercury, whatever it is. The last thing, what about the little I? So where does that fit into this whole thing? I would put it right up here. Number of moles of solute times the Van Hoff factor, right? If sodium chloride, then that's going to multiply it by 2. That's actually related to molarity times I. It's kind of thinking about how this fits together.
just a quick clarification, that pi has nothing to do with the actual number of pi then?
Nope. This is not the mathematical number pi. Pi, a lot of things in chemistry are represented by Greek symbols. Pi is one of those symbols. So that symbol represents osmotic pressure. So you guys will have homework for class on Wednesday that utilizes osmotic pressure, define molar mass, and Rayleigh's law a little bit again. Feel free to post questions on Blackboard. Hope you guys have a good lab.